Buenas tardes a todos. Para mí es un placer, verdadero placer, presentar al profesor Martin Asplund, que es un gran especialista en astrofísica, un gran especialista en abundancias químicas, en propiedades de estrellas y, además, en este ciclo tan especial que es la ciencia del cosmos, la ciencia en el cosmos. Porque verdaderamente los astrofísicos tenemos un problema que también es una virtud. Nosotros no tenemos laboratorios en los cuales podemos ir y repetir experimentos. Nos tenemos que limitar con mirar unos puntitos de luz que están en el espacio, que están en la esfera celeste, y a partir de esos puntos somos capaces de extraer una grandísima cantidad de información. Es verdaderamente, para mí, una epopeya, es fascinante que seamos capaces de derivar propiedades químicas, de derivar edades de estrellas, de saber, en definitiva, cómo se ha formado el universo. Y en varias de las materias el profesor Asplund es verdaderamente un especialista reconocido a nivel mundial. En estos laboratorios, que a veces además nos proporcionan condiciones extremas que no podemos reproducir en la Tierra, como he dicho, somos capaces de ver unas propiedades que nos cuentan historias sobre el origen de las estrellas y el origen de la materia de esas estrellas, de los elementos químicos que forman las estrellas, pero también los elementos químicos que nos forman nosotros, porque somos verdaderamente, y no por mucho que se diga, deja de ser cierto, hijos de estrellas. Y él nos va a contar técnicas, nos va a hablar de ciertas técnicas que se empezaron a descubrir a principios del siglo XIX con el examen del espectro del arco iris del Sol, la detección de bandas, de líneas oscuras denominadas líneas de Fraunhofer, que a lo largo del siglo XIX se empezaron a identificar con elementos químicos y que ahora somos capaces no solo de conocer qué son, cómo se forman, sino que conectan, como he dicho antes, el origen del universo con nosotros mismos y que las nuevas técnicas, además, nos permiten detectar en las atmósferas de exoplanetas, planetas fuera del sistema solar, y que en realidad no vemos directamente, pero conocemos sus propiedades. Así que en esta fascinante historia creo que el profesor Asplund nos va a ilustrar y nos va a dar una excelente conferencia que creo que nos va a deleitar a todos. Muchas gracias.
Thank you very much for this invitation. And first of all, thank you very much for the invitation to come here. It's a real pleasure and a privilege for me to be here and give this talk. And I would like to thank the Foundation very much for the kind invitation to come here. And I also like to thank the audience here for deciding to come here on a Monday evening rather than enjoying a wonderful evening out in Madrid. And instead come here to hear about a cosmic journey that I will try to tell you about, something to talk about the origin of where we all come from, the different elements, and where they come from in different stars, or indeed in the whole Big Bang. So what I'll try to talk you to in this evening presentation is to try to give you a journey about where the different elements are coming from. So we probably have all wondered at some stage or another, where are we all coming from? So where is the carbon in our bodies? Where was it produced? The oxygen that we breathe? The iron in our blood, or for example the lithium in the batteries that we use in our laptops. It turns out that all of these are produced in stars or in the Big Bang, and I will try to explain to you in this talk how this actually happens. Now, if you look out in the night sky today, in the evening, you see lots and lots of stars, and you may see some planets, Mars, Jupiter, and so on. If you have a telescope, or at least a binocular, you may see further away out in the galaxy. You see more and more stars. You may even see some galaxies. So galaxies are whole assemblies of stars. Now, astronomers nowadays, we use bigger and bigger telescope. And the reason why we do that is that we can able to look further and further away. Now, in astronomy, when you look further and further away, that also means that you look backwards in time. Because light travels with a finite speed, that means that it takes time from the galaxies, the light from the galaxies, to reach us and the telescope that we use to observe them with. That means that as we look further away, we also look backwards in time. And this timeline is trying to explain what you actually do, how this actually happens. So today we see the galaxies around us, but as we're looking further away, we're starting to see it backwards in time until we're actually seeing the first galaxies that were formed that happened about 13 billion years ago. This is what we're actually starting to see now with the biggest telescope that we have today. If you go even further backwards in time, you see something called the cosmic microwave background. That's kind of like the baby picture of the universe that we see today. That's the afterglow of the whole origin of the universe in the Big Bang. Now that was originated about 400,000 years after the Big Bang. We can't see further backwards than that, but we know that in the early days of the universe, everything was very, very compressed. And we see the galaxies nowadays are moving away from each other. And this is a remnant of the explosion that actually created the whole universe. It created the space, and it created all the material that we see in the universe today. And this is then the Big Bang. Now, this was realized quite a long time ago that we have this fireball origin of the universe. And in that moment, the first few moments after the universe was created, the temperature was so high and the densities were so high that you can actually produce elements. And this was something that was realized by George Gamow, and he proposed that all the elements that we see today was actually produced in the Big Bang. Now that turned out to be incorrect, as I'll try to explain in a moment, but it actually turns out that from the initial protons and neutrons that you have available, you start producing some of the elements. You produce hydrogen, you produce helium, and you produce a little bit of lithium in the first few minutes that happen after the Big Bang. Now, this almost works like a nuclear reaction. Nuclear reactor, you take light elements and you produce heavy elements. So you start with proton and neutrons, as I said, and then you end up with hydrogen, helium, and a little bit of lithium. Now, this is a very flawed nuclear reactor. Because the universe was expanding so quickly, the temperature was decreasing very rapidly. So after a few minutes, the temperature was not high enough that you can continue having this nuclear burning happening. And the densities was not high enough. That means that you can only have time to produce some of these elements. You didn't have time to produce heavier elements like carbon and oxygen. You simply did not have enough time or temperature and densities in the early moments of the Big Bang. So basically, this nuclear reaction network finished at some stage with the end product being lithium. You couldn't produce more elements like that. Now, exactly how much you produce of hydrogen, helium, and lithium depends on how much material there was in the universe. So if you had lots of material, you could produce different ratios of different elements. And this is what's trying to illustrate here. This is how much material there is in the universe. You can think of this as the density of material in the universe. And this is what you would produce if our understanding of the Big Bang was correct. So the different elements that you produce was helium, helium-3, which is a different isotope of helium, and lithium, and then a deuterium, which is an isotope of hydrogen. Exactly how much you produce of these different elements depend on how much material there was in the universe. So you can then use this as a probe of the Big Bang. So if you can go back and study the very oldest objects in the universe, stars, for example, that haven't been modified after since the formation shortly after the Big Bang, you can then reveal how much material there was in the universe. So this is a way to measure how much matter there is in the universe. So the idea here is that you try to measure, for example, the lithium content in the very oldest stars that we can see today. And from that, we can then deduce how much material there will be in the universe. And this is one of the foundations for why we understand and why we believe and why we are so certain that the Big Bang actually happened. Because this has been proven to work very well overall. And this is one of the foundations, one of the pillars of the Big Bang theory. Now, more recently, well, I'll just try to explain this. To me, it's very fascinating that you can actually try to measure how much material there is in the universe just by determining how much lithium there is. So to me, that's quite remarkable, and I hope you will understand that too. Now, more recently, the last decade, there's been a completely different way of viewing this. There's an alternative way of measuring how much material there is in the universe. And what you use then is this cosmic microwave background. As I mentioned, this is the baby picture of the universe. So this is the afterglow that happened after the Big Bang, and where the material started to shine through. And this will happen about a few 100,000 years after the Big Bang. Now, this is a map of this cosmic microwave background. And you see this variation. This is basically temperature variations. These are reflecting the density inhomogeneities that was seeded at the Big Bang. And all of these eventually turn into and growing with time to become galaxies or clusters of galaxies. Now, how much you have of this variation actually depends on how much material there is in the universe. So this is a completely different way of measuring how much matter there is in the universe. And in fact, this is a much better way of doing it than using these light elements that I was talking about just in a moment. So these kind of observations from the microwave background and also types of supernova explosions and so on reveal a completely different picture of the universe that we have today. We now know that material that we consist of, all the atoms, the normal material that we all consist of, it's only a small fraction of all the material there is in the universe. We also have what's called dark matter. We don't know what it is, but it makes up about 1/4 of all the material content in the universe. And then in addition, we have something called a dark energy, which we really don't have any clue what it is about at all. And these are really fascinating talks, and I will not talk about that here at all. So instead, I will focus only on the normal material that we see, what we are made of, the normal atoms that we all consist of. Now, as I mentioned, this is the density of the matter in the universe. So we now know we can measure this exquisite precision using the cosmic microwave background. So you can then turn the argument around and see, does that picture then hold together? If we then can predict, if we understand how Big Bang works, we can predict how much lithium the stars should have, how much helium they should have, and so on. And it turns out that, yes, indeed, it works very well for hydrogen and helium. It does not work very well for lithium. And this is a big problem nowadays. We still don't understand it. That if the lithium that we see in the older stars is too little compared to what was predicted to have been produced in the Big Bang, by about a factor of 3. Now, I'm not saying that the Big Bang was wrong, but I'm saying that it may be that the Big Bang picture that we have is maybe too simplified, that we need to expand it a little bit, modify it perhaps. And there are ideas that this could happen because you have supersymmetric particles, so elementary particles that are predicted to exist. We don't know whether they do or not, but if they do, they could have modified how much lithium in particular that was produced in the first few minutes after the Big Bang. Now that's very speculative, and it's very exciting if that would be the correct. Now there could also be a very much more mundane explanation for this lithium problem, namely that we don't understand the stars where we observe lithium. Maybe the stars have destroyed lithium. So this is very much an open question nowadays to try to understand this cosmological lithium problem. Is it a problem with Big Bang, or is it a problem that we don't understand the stars correctly? So, as I mentioned, the only elements that you produce in the Big Bang was hydrogen and helium and a tiny, tiny amount of lithium. So this is showing on a logarithmic scale. So remember, you produce lots and lots of hydrogen, a little bit less helium, and then very, very little lithium, but nothing else other than that. But of course, we all know that we have all the other elements here. We all consist of carbon and oxygen and so on. Where were they produced? And it all turns out that we're produced in stars. So as Carl Sagan used to say, this is a famous astronomer, he used to say that we are all star stuff, meaning that we were all originated from material that were produced in stars, in the really hot interiors of stars. And the next few minutes I will try to explain how different types of stars produce different types of elements and how we can use that in order to learn something more about the universe. So indeed, this is what happens in our own star, namely the sun. The sun is burning hydrogen and turning it into helium in the interior. The temperature is so high that this is what happens. Now, what actually happens is that you're turning 4 protons into helium. But the mass is slightly smaller for the helium nuclei than for the 4 protons. And that mass difference can be converted to energy using the Einstein E = mc squared. And this is the explanation why the sun shines today. Now this happens for a very long time. We have lots of hydrogen in the sun, and they will burn for a very long time. So basically almost 10 billion years. So 10,000 million years it will happen like this, more or less the same way it's burning nowadays. So it's a long way away. You don't have to worry about it just now. Now after it has been burning, you have turned hydrogen into helium, the next step is to convert helium into carbon. And I mentioned this is very difficult to happen in the Big Bang because you didn't have enough time, you didn't have enough temperature. In a star, on the other hand, the stars live for a very long time, so you can overcome this problem that you cannot actually produce carbon that you couldn't do in the Big Bang. And something that is quite remarkable was discovered by Sir Fred Hoyle, the famous astronomer. He realized that because we exist today, we know that carbon must have been produced this way. So what actually happens is that you take 3 helium atoms and simultaneously collide them together. This is a very unlikely process, and this was a problem that we didn't understand how we could actually produce carbon this way. But he realized that there must be a very specific nuclear property of this intermediate step, which is called beryllium, that you have to have beryllium in order to get carbon. And he predicted that it has to have this very, very unique special feature in this beryllium nuclei in order to get to carbon. And after a while, after a year or two, they actually experimentally discovered this. And the whole reason we exist today, here, and we're sitting in this room, is the fact that this particular nuclei of beryllium-8, which is a completely irrelevant nuclei in most properties, has this very, very special, unique property. And this is quite a remarkable thing. If it didn't have that, we wouldn't be here today. Now, what then happens as the star evolves, it's then continuously turning lighter elements into successively more and more heavy elements. So you're turning first hydrogen into helium, helium into carbon, and then eventually you go carbon to nitrogen, to neon, oxygen, magnesium, and silicon, and eventually up to iron, if the star is massive enough. Now, our own sun is not massive enough, so that will actually stop at this stage. It will only turn helium into carbon. It's not enough dense in order to go to these heavier nuclear burning reactions. But if the star is very dense, very massive, it will reach the stage where it produces nickel and iron. But that's the end product. You can't go further than that in a stellar evolution. At that stage, the star is doomed, and it has to explode in a very explosive death. And I'll come to that just now. So what actually happens then is that throughout these different burning products, you're turning lighter elements into heavier, you actually release energy, and that makes the stars shine. But at that stage, once you have produced iron and nickel, you can no longer generate more energy. It will actually take energy in order to produce them. And this is what happens. At the end phases of the stellar evolution, you're starting to suck energy away from the interior of the star. And that means that the whole star starts to collapse. The interior starts starting to collapse. And when it happens, eventually you're turning the interior parts into what's called a neutron star. So it reaches nuclear matter. And it can't be more compressed than that. And that generates a shock wave that is propagating outwards. And that's then exploding the whole star. Now, that sounds very simple, but it's very, very complicated how you do this. Nature knows how to do it. Astronomers do not. When we use computer models, for a long, long time has been a problem. We can't actually generate these supernova events. So these are the explosive deaths of stars. This is one of the simulations showing here. And what actually is shown here is the innermost part of this massive star. So it's not showing the whole star. The whole star is several thousand times bigger than what's actually shown here. And it's color-coded in different temperatures. So you have this initial reaction where it starts compressing, and it starts then generating a shock wave that is propagating outwards. But you notice that it doesn't get much further than this. The surface is much, much wider than this. So the explosion at this stage stalls. It doesn't get further than this. And that has been a problem for decades. Astronomers don't get the explosions that we see in nature, and we don't understand why. And it turns out that more recent simulations, you can actually start getting more and more slowly. Well, I shouldn't say slowly, because you have the time scale down here. The whole movie that is shown here takes less than a second in stellar time. So it's a very, very fast process. But at the end of this simulation, you start seeing that it's starting to expand further and further outwards. Now, at that stage, they ran out of computing power. They couldn't simulate it further. Even on the biggest supercomputers there are in the whole world, they could not simulate it further. But they can predict and see that this is an explosion that will continue. And eventually, after a few seconds or a few minutes, it will actually disrupt the whole star. and this is what will happen. So the different elements that I'm talking about today, I will try to illustrate that they are produced in different types of stars. So stars like the sun is a relatively low mass star, it's not a very heavy star. They live for a very long time, and they produce elements like carbon. More massive stars, they have more fuel to burn, but they do it much more vigorously. So they burn their fuel very quickly, and they actually live very short. And they produce other elements, like nitrogen in this case. And as we just saw, we have this supernova, the explosive deaths of very massive stars. They live very short, and they produce elements like oxygen and iron. There's also a different type of supernova that I will try to explain just now that happens in a completely different environment. They have in a binary star, you have a small star, a remnant from in a white dwarf. So this is a stellar remnant of the sun, for example, in 10 billion years or 5 billion years time from now. It will contract to become a very small, dense white dwarf. If that white dwarf is accreting material, it's from a companion star. This is the companion star, and the white dwarf is a very small thing in the middle there. If it accretes enough material, it can generate an explosion at the end, if it reaches sufficiently high mass. That happens on a very long time scale, on billions of years, and that produces particular elements like iron. So what I'm showing here is one of these movies, one of these computer simulations for this kind of event. What I'm showing here is only the white dwarf, and now it's accreting material from a companion star. You don't see that here. And the size of this kind of white dwarf that is shown here is about the size of Earth. And the time scale that is also shown down at the bottom here is on the order of a few seconds. And in the beginning, it starts burning nuclear fuel in the interior of this white dwarf. And at about 2 seconds here, just in a moment, it will actually start disrupting the whole white dwarf all of a sudden. That's when it happens. And that's in that instance, you produce lots of elements like iron. So these are the kind of supercomputer simulations that astronomers use nowadays to try to predict how different supernova happens and what kind of elements are produced in these supernova events. So iron, for example, that we now have here, it actually turns out that that produced both types of supernova. And it just happens to be that about half of all the iron that we have here on Earth comes from this first type of supernova, which is deaths of very massive stars, and about half of it comes from this supernova that happens in a binary system. And it just happens to be about 50-50. Now, what about all the elements that are heavier than iron? I said that you can't produce heavy element than iron in a normal stellar evolution because it takes energy. You don't release energy when you produce it. So, but we have all those elements, so where do they come from? And it actually turns out that those elements are produced by successive captures of neutrons. So in certain environments in stars, you can actually bombard iron nuclei successively very, very rapidly and produce more and more neutrons, and that will grow the iron nuclei to become bigger and bigger and eventually become elements like iron, elements like lead and gold. Certain types of these very heavy elements are produced in stars like the sun, in the distant future of the sun. Like the sun will expand when it reaches towards the end of its lifetime and become bigger and bigger to become a giant star. And at those phases, you can produce certain elements like lead. Now, elements like gold, on the other hand, are produced in a completely different environment. They are produced because you have an enormously high density of neutrons available, and therefore you can produce these elements like gold. And it has for a long time been believed that they were produced in connection with these supernova events, but it never worked. For several decades, people tried really hard to find these kind of supernova simulations in order to generate the gold that we see today, but it didn't work. But very recently, just the last couple of months actually, people in my group in Germany had developed very sophisticated computer simulations where you have two neutron stars that are orbiting each other, and eventually they are coming closer and closer together, and eventually they collide with each other. And when they collide, they generate lots and lots of energy, the temperature enormously high, and because you started off with such a high density of neutrons, you have these neutron stars, you have exactly the environment that you need in order to bombard the iron nuclei to turn it into gold and other elements. So this is quite a very, very fascinating development in astronomy just the last few months. So in this very short expose, I'll try to explain to you that all the different elements that we see today, the carbon that we have in our bodies, the oxygen we breathe, the iron in our blood, and so on, each element has its own unique characteristic. It has each unique cosmic origin. They're produced either in the Big Bang, or they're produced in different types of stars in different environments. So we can then use this information in order to learn more about the universe. We can learn, of course, about the stars themselves, how they produce the different elements, but we can also use it to learn about the Big Bang, as I mentioned about lithium, but we can also learn about galaxies and how galaxies like our own Milky Way galaxy has formed and evolved with time over the last, say, 13 billion years ago. And the way we do that is we're using something called a cosmic recycling. All the material is continuously going from the interstellar medium, so the gas between stars, and turns into stars, and eventually gets back into the interstellar medium. And this is a grand recycling scheme. So what actually happens is that you have gas clouds out in space. If they are dense enough, they start contracting, because with gravity you pull things together. If you have sufficient amount of material available, you will have enough temperature to actually ignite hydrogen burning. So that's when the star is born. And then, of course, the stars continue living for a long time, depending on how massive they are. Either live for a few million years or up to several billion years or longer. But eventually they will die. Okay, so I just try to explain to you. The sun will more or less just fluff out and end its life. But then some stars will die in a very explosive supernova death. But as they die, they return some of this material that they were born with out into space again. And in addition, because they have produced some of these elements in the nuclear burning, they then return enriched material back into the space again. So the material that they return contain more of the heavy elements than they were born with. So that means that for each cycle you go around like this, you go from the space into stars and back into space again, you generate more and more heavy elements. And how quickly you turn material from light elements to heavy elements depends how quickly you go around this cycle, how much stars you form at any given time, and it also depends on what element that you're looking at. Some elements take longer to produce than others, depending on the timescales involved. So we can actually use this to try to piece together the history of a Milky Way or any other galaxy. It's a little bit like archaeology. Archaeologists, they dig for relics in ground to try to piece together the history of a culture. So you look for different relics in ground, different locations, different places that you may be interested in. We do the same thing with stars, because the stars still contain the material that they were born with. And we can use that information to piece together the history of a galaxy. So in this sense, the stars work as a probe of the cosmos. And in particular, the chemical compositions of stars are a very, very good tool for us to learn about the history of a galaxy or a star itself, or indeed the whole cosmos. So the way we do this is that we use the chemical fingerprints that are imprinted in the starlight that we see. If you look at the sun or any starlight, it contains different wavelengths. Just like you can use with a rainbow, you split light up into different frequencies, different wavelengths, to have different colors. This is the same thing what astronomers do, but of course in much more detail. The starlight that we see, we can split up in an enormous amount of different wavelengths, and each one of these will be able to contain the traces or the unique fingerprints of all the different elements that we see today. So this is what's shown here in this figure. You're splitting up in this rainbow color. You have these dark bands. It's like a barcode, but that barcode is reflecting how much you have of different elements. Each one of these different dark bands is coming, or originated in a certain element, a different atomic transition there. And exactly how strong these different bands are depend then on how much material that you have of that particular element. So from this information that you have in the observations, you can deduce how much the different stars contain of different elements. So this is what we're trying to do. Now, it's not as simple as with a barcode you can read off a price immediately. It's unfortunately not quite that simple. Instead, you have a very good understanding for how the stars actually emit the light that we see. And we have to use computer simulation for doing that. Because if you zoom in on the sun and the solar surface, you see that the sun is not a very simple object. You see that it's a completely dynamic process. So this is the solar surface that we see. If you zoom in further and further and further, you see this kind of process like this. This is the observational manifestation of something called convection. So you have convective boiling motions at the surface layers that are continuously evolving with time. The light areas here, they are gas that are warmer than the surrounding material. Each one of these is about as big as Earth. They give you a time or a length scale involved here. And they typically evolve on a time scale of a few minutes. So in order to do this, to try to predict the spectrum, you have to explain this phenomena very well in order to get a realistic determination of the chemical elements. And indeed, this is what we can do nowadays. So this is one of the supercomputer simulations that we are doing in my group. So we are trying to simulate not the whole atmosphere of the star. So the atmosphere is the surface layer that is actually emitting the starlight that we observe. Instead, we're taking a small part on the stellar surface and try to simulate that using supercomputing simulations to try to predict how the gas moves and how they emit the spectrum, the light that we see. And if we have a very realistic model for this, we can then deduce how much of the different elements there are in the stars. So one of the things that we have been doing over the last few years is to determine the chemical composition of the sun very, very accurately, much more accurately than what people have done before, because we have these more realistic models for the stellar or the solar atmosphere in this case. And it actually turns out that to our surprise and to everybody else's surprise, the sun actually contained less heavy elements than what people thought beforehand, by about a factor of 2, almost a factor of 2 less than what people thought beforehand. So the sun contains about 1.5% of heavy elements. So heavy elements are everything heavier than helium in this case. So about 90% is helium, about 10% or just under 10% is helium, and the rest is everything else. But that little bit less, everything else, so this is carbon, nitrogen, oxygen, iron, and so on, is less than what we thought beforehand. It's about 1.5% only. And that actually has some very profound implications for astronomy, because astronomers, they always use the sun as a reference. They use it as a yardstick in astronomy. So whenever you try to determine the chemical composition of a star or a galaxy or whatever, you always do it relative to the sun. So it's like changing the yardstick that we have in astronomy. If the sun contains less heavy element, that means that all the other objects in the universe actually contains less heavy element as well, because we use the sun as the measuring stick here. And this is a big debate at the moment, whether our results are correct or not. If there are astronomers in the room, not everybody believes what we are doing is correct. I'm fairly convinced that we are, and most people are now starting to agree with us, I would say. But this is still it's an ongoing debate at the moment. But that's a technicality. But what I'm trying to illustrate here is that we can actually determine very accurately the chemical composition, not only of the sun, but of stars in general. The next question you can ask then yourself, is the sun unusual in any way? Now, the sun, in many ways, is quite a typical star. It's maybe a little bit more massive than most stars. Most stars tend to be a little bit smaller than the sun. But it's not unusually or very, very much more massive than most stars. It's also a little bit unusual in the sense that it doesn't have a companion star. Most stars that we see today seem to have been orbiting together with a companion star. But the sun, of course, is a single star. We don't. But it's not particularly surprising. But the interesting thing here is then, could it be that the sun is unusual in its chemical properties compared to other stars? And people have looked for this for quite a long time, and particularly has been a big effort over the last 15 years, since the first extrasolar planets were discovered. So most of you will know that we know about planets outside the solar system. It's about 500 of those stars that are known today that are orbiting other stars, more or less solar-type stars. And people have then tried to understand, is it possible that we can tell whether a star has a planet because it looks a little bit different in its chemical properties? And people have tried this for ever since the last 15 years, since the first extrasolar planet was discovered, and not really come up with any substantial evidence that they are different, that could reflect the fact that there has a planet or not. But very recently, what we have tried to do is exactly this. And because we have more realistic models, and we can then derive the chemical composition more accurately than what people have thought before and or achieved before, we can actually see very subtle differences, but they are significant. And we can actually compare the sun with stars that are supposed to be completely identical to the sun, and we still see subtle differences in its chemical compositions. So it's like a particular fingerprint that we believe is a direct result of the fact that the solar system has planets. So our idea here is that when the sun was formed, you also formed the planets in the same time. Some of the material that ended up in the planets, of course, didn't end up in the sun. Some of that material in the planets were locked away, and that material we can see the evidence of in the chemical composition when we compare the sun with other stars. At least that's the idea that we have, and we are now trying to prove this. It's a speculation at this stage, we haven't proven it, but if it's true, it opens up a completely different way of studying planets around other stars. There are two different ways of finding planets as it is now. We have the radial velocity technique, so you can see that the star, if it's orbiting around with the planet, the planet will tug the star backwards and forwards ever so slightly, and you can detect that variation. You can also see if a planet happens to pass by in front of the star in the line of sight to us, it also makes the star light decrease ever so slightly. Now, this would be a completely different way of trying to find planets around stars, or at least to try to find stars that form planets. Whether they have planets at this stage or not, we don't know, but they were quite likely that they did form planets. And this, to me, is very exciting, and this is something that we will try to push further in the coming years, because this is really a completely new way of trying to find stars with planets. Now, let me just finish off this talk to move over to the other side of this story, namely the planetary atmospheres themselves. So until now, I've only tried to explain to you how we deduce the elemental composition of stars. But we are now at the real verge of being able to do exactly the same thing for planets around other stars. We are able to find the signatures of the planetary atmospheres in the light coming from the planets. And this was achieved just in the last few years. So this is detecting the atmospheres of planets around other stars. What's shown here is one of these very early detections that we are now starting to see this. So what's shown here is a different wavelength. So this is in the infrared region. And this is the flux from the planet relative to the star. And you notice that these are very, very subtle differences that we see in order to detect the planet, because the planet is extremely faint relative to the star. So it's extremely difficult to do this. And that's why these error bars are quite large. But what we're actually starting to see, in this particular case, this happens to be one of these extrasolar planets, we're starting to see signatures that are stemming from the atmospheres of the planets. And we're starting to see the signatures of different molecules that are in the atmospheres. In this case, we may be able to see evidence for water, carbon dioxide, and carbon monoxide, and so on. This is truly remarkable, in my opinion, that we are now at the verge of detecting what other planets consist of, or at least what the atmospheres consist of. And this is, of course, a field that will really explode in the coming decades, where we'll be able to do this in much, much more exquisite detail than what we are only able to do right now, because this is very much early days. Now, what we want to do is, of course, to find signatures for life. That's the ultimate goal. Could we find one of those planets that have a specific spectral signature that is really reflecting the fact that it has life there or not? So this spectrum here is actually the Earth, seen from a spacecraft, in this case from Mars, looking back at Earth. What does the Earth atmosphere look like? Could we see signatures that is telling us that there is life on Earth? In this particular case, you have features like ozone here, you have water, of course, and you have different oxygen molecules. Ozone, for example, is predicted only to be really related to life, and you also have molecules like methane. Is it possible that in some few years from now, we'll be able to do exactly the same thing for other planets around other stars? To me, this would be incredibly exciting if we can. We may not be able to say that they have life, but they at least have the ingredients that seem to be necessary to have life. And this is what will happen certainly in the next decade or so. Because astronomers, we are developing more and more sophisticated telescopes that will be able to do these kind of observations and other types of observations to learn more about the universe. Two of the most fascinating new telescopes that will become available over the next decade are these two illustrated here. One is the James Webb Space Telescope. It's being built by NASA in the US, and it will fly in 2018 if it's approved, fully funded, and so on, which is somewhat debated at the moment. But we all, astronomers around the world, are certainly hoping that they will go ahead as planned. And in that case, they will be able to detect more and more of these planets, and they will be able to tell spectra on these planetary atmospheres to find exactly these kind of signatures that we are looking for. We also have in Europe a fantastic new instrument or new telescope that we are just starting to build in Chile, which is called the European Extremely Large Telescope. Now, astronomers are not very innovative when it comes to naming telescope. At the moment, we have the Very Large Telescope, and the next telescope will have to be the Extremely Large Telescope. And then I guess there will be Overwhelmingly Large Telescope or something like that. I should mention there's also a completely different telescope, which is very small, but has a very niche instrument, and that's called the Very Little Telescope. So this telescope is it's mind-bogglingly large compared to what we have today. So just to illustrate, this is showing one of these jumbo jets. Now, I'm not suggesting that they will land a jumbo jet right next to it, but this illustrates the scale that we're talking about here. So the mirror of this new telescope will be 40 meters in diameter. The biggest telescope that we have today has a mirror that is 10 meters. And this will be 40 meters. Now, it will not be just one mirror. It will actually be segmented mirrors. You have several mirrors that you put together. But in total, it will be 40 meters wide, which is just enormously big. And the engineering challenges involved here is extraordinarily tough. And you have to take into account how the wind will blow and things like that can move around this telescope. So it's extremely difficult to do. But this is something that we hope will be built over the next decade, if it's being approved in the next year by ESO, the European Southern Observatory. And together, these kind of telescopes, and also other similar types of telescopes, there are, in the US, there are two types of these, a little bit smaller telescope, but they will also be built. Together, these kind of telescopes will really revolutionize astronomy, and it will open up a completely new way of how we see astronomy. And to me, the most exciting thing would be, of course, is that if these kind of telescopes will be able to show us the signature of life. Now, that may be unlikely that exactly this generation of telescope will do, but it will certainly be a long way ahead. We're moving ahead. So that will conclude my talk, and I hope I'll try to illustrate to you that you all in this room have some cosmic origin. All the material that we have in you are produced in the Big Bang. They're produced in stars of different types. So I hope that will give you a cosmic perspective on life. So thank you very much for your attention.